So for the snow sloughing lab, we annotated the original lab so that it's easier to see all the equations that's required. So I'm here with Logan. We can go through this.
Hello.
The first thing is that we had cost effectiveness CE, but now it's easier to see with a numerator and denominator, so we're calling it snow sloughing as SN and roof cost as RC. The numerator SN is defined here, K1 sine squared theta, except
There's a hint at the bottom of the document that says to do it only in terms of H.
yeah, exactly. And then whenever there's that theta, we have to replace it. So in the drawing here, we need to use geometry to know how to make this in terms of x and h. So on the right side, we've got the sine theta can be is like opposite over hypotenuse, and then you square that, and you end up with this k1 sine squared theta equals
Well,
k1
how did we
cos
get
h
L
squared.
as L you get
Yeah.
L from just Pythagorean theorem.
Yep. So this one right here, L is the same as uh, x squared plus h squared.
Well, you have to square root that, but yeah.
There we go. So every time we saw L in here, we also replaced it. So we end up with this k1 h squared divided by h squared plus x squared.
Bringing in the K1 from the equation
Yeah.
for SN.
Okay, so we covered how to simplify the numerator, and then we have to cover how to make the denominator. So the denominator of roof cost is cost of EP plus cost of SP. That's end panel plus side panel. So they define it here. CP equals K2 times 2 times 2x plus 2L. Again, that L we have to replace with x squared plus h squared from geometry, and then it should be okay. So you end up with this right here. And then SP, the second part of it, there's also an L. You have to replace that. So you end up with this equation. So you have to do CEP plus CSP. You add up these two, and then that's your denominator roof cost. So algebraically, we got this down. Like we understand this equation, the overall equation. What we're trying to do is optimize it. So from the diagram, if your h changes, like the height of the roof changes, the angle also changes, they're telling you to figure out what happens if your angle goes from 10 degrees to 80 degrees. Like if this roof gets super steep like that, what happens to it? And what happens is that the cost effectiveness changes. And also the cost and the snow sloughing ability. Like everything changes when you change this h. And also in this diagram, they give us all these constants. So um, if you redraw that diagram, I just wrote down what the constants are. So x is constant, d is constant. So though, like we don't have to worry about L because we did everything in terms of x's and h's. And we even have this note here: make everything in terms of x and h. Um, yeah, including the
Well,
angle
oh, go
too.
for it.
Yeah, including this one, we make this in terms of um, like x's and h's. So tangent is opposite over adjacent. So tangent h over x. We can do that. Use that equation to solve for h right here. So h will be x times tangent a. So that this angle is still this, like it's still here, but it's going to vary from 10 degrees to 80 degrees. So we plug that in to this equation. So that's another equation that you'll need. But yeah, according to this diagram, we have constants where we have h is unknown, and then we have the angle varying from 10 degrees to 80 degrees. Uh, yeah, any thoughts, Logan?
I had not realized about x being equal to no h being equal to x times the tangent of a. So I I
Yeah,
do I do want to know though, since we have x as a variable, we're not even really playing around with the angle a as a variable, right? We're only varying h, right? At least in
we're
our code.
varying, we're changing according to the question, like if this angle right here, theta,
Yeah.
changes
If that
from,
were to change, the
yeah,
height would also change. But if you also change the height, the angle changes too as a result.
yeah, yep, and then this relationship here. So we'll need to put this in the code because everything is in terms of x's and h's.
Okay.
So that helps us because instead of putting in angle in our code, we'll put h. So that's a good explanation of this part right here. The solution to like if you change the height of the roof, it will change the cost effectiveness. It's here. So you'll eventually have to plot this and figure out how like what to do with the graph. So on the x-axis we have roof height. Um, so it ranges from that like from 10 degrees to 80 degrees here. It changes the h, which we found from that h equation. We'll recap that, but we just vary the roof height for the x-axis from 0 to 100 feet. So as this roof gets taller and taller, the cost of it changes, the cost effectiveness.
So we plotted CE against H.
Correct.
Okay.
Yeah, and then that's how you get this graph. And let's say you do like a 60-foot height roof, you have a cost effectiveness around here. So it says point whatever 0002. Uh, or actually, if you read it from the graph, my bad, it's a little easier. 2 point something. And then over here is the max cost effectiveness. So that means this is an optimization problem. So the max of this graph gives you the optimal, x variable. So since this is the max here at 20-ish feet, we have the most cost-effective roof, 3 point something. And if I plot it, um, sorry, if I run it, oops, oh here we go. If when I run it, it states it here with this print function, optimal roof height 21 feet, and the max cost effectiveness here, 0.0036. So it's the height, max height. Okay, we'll just go through the steps of how to get this graph from all the algebra.
Where specifically
So
in the code, just real quick question. Where
yep.
in the code is the H equals X times the tangent of A?
Oh yeah, up here. So
Oh, that's it. Okay. Okay. Got it.
yeah, it's like plugging in the angle min and angle max. So guess these are your bounds. So instead of saying angle 10 degrees, angle 80 degrees, we're making a graph where the bounds are the height minimum at that's created by the angle 10
So we're
degrees.
following our hint and making H the variable, but by doing so, we can no longer use A. So we gotta use the A to find the H.
Yeah, if we were to simplify this, I can say here, like make a plot. X-axis is height,
Yeah.
height of
Okay.
roof, and y-axis is cost
CE.
effectiveness. For x-axis, you'll need the bounds of it. So bounds are from angle, what is it, 10 to 80, but make it in terms of h.
That's
Like,
good advice.
yeah, that's how I see it. Okay, we can make this from scratch and go line by line so that it's clear. And I'm gonna just do run um, new snow slough lab solution. Okay. Uh, we start by doing parameters. So I'll do a mix of copying and pasting the solution so I don't have to spend time typing everything. So it's like this is declaring all the parameters. So according to the layout, um, we're given the equations and then these givens right here. So we can plug these numbers directly into the equations.
And then also the angles too.
Yes, correct. The angle. Thanks, Logan. So we got um, right here x equals 15, and then we can describe what it is with a comment base in feet. K1 equals 39. Oh, I also put the semicolon. K2 equals 45. D equals 55. K3 equals 24. So K1 is just like a constant. K2 is constant, also, but it's also let's say unitless constant. K2 is end panel cost coefficient. D is the depth of panel. And then K3 is the side panel cost coefficient. Okay.
Minimum angle is 10 degrees, max angle is 80 degrees.
Yeah. Cool. Min angle and max angle. I call it A min and A max. Okay, and then from our equation we did.
Since h is our variable, we have to find the h's for all of our known angles in the range.
Correct. So we'll do h min as a lower bound. We said it was x tangent A, so x tangent, and then we'll do degrees, and then A min, whoops, with argument. Okay, and then h max, same thing, x times tangent degrees A max. And then now we can make the numerator snow sloughing numerator. That would be Sn equals, and then since it's a function, like it has inputs, and the main thing that we're varying is the h, we'll need to do the at h. So it's like this, the shorter notation of a function. Then in parentheses, or you can avoid the parentheses too if you want. Like we need to start writing the function. So according to Sn, the numerator, right here, we said it's k1, so we got k1 times h squared, and we'll do the dot square since it's element by element. Like everything I'll do here is element by element. So that's the numerator, then divided by h squared plus x squared, so h squared plus x squared. Actually, the x doesn't need a element by element. X is constant. Okay, so k1 times h squared divided by h squared plus x squared. That's our Sn. And then we'll need to do the denominator now. Proof cost denominator. And that's these terms. So if I were to simplify that, it's RC as a function of h. So it's like at h, but then we got these terms right here, CEP, CSP. C, this is a comment because I'm just showing the overall structure without having to type it in. So I'm going to copy and paste this. So again, it's a function of h. Then we have the CEP as this first term, and then CSP is the second term. I'll put it side by
So
side.
you could make you technically could make two different functions and then add them up into another function, but that would just be a lot more work.
Yeah, we could do that, like CEP, CSP. As long as you're confident that you wrote this right, it would work
Okay.
out. But yeah, actually, that's what we did with breaking it up into numerator and denominator. Like you could do it, like you've seen this before, like you can do it without breaking it up into numerator and denominator and have it as one giant equation. So k2, 2 times 2x plus 2 square root x squared plus h squared, and then make sure the h's have the element by element um, operation, the dot. And then we got k3 times 2d, so that's over here, times square root x squared plus h squared. Okay, that looks good. Then now we need to do the overall equation. So overall cost effectiveness equation. That's going to be CE, and then I'm doing the at h. That's our what we're varying again. Then it's the numerator SN H, and then dot divide RC H. Okay, we have the main equation now, and that's our like the y values of the graph. Then we can go into optimization. So we need the maximum of this thing, and usually we will store it as the h optimal variable, and then we'll do f min bound, and that's so like we need the function and the bounds. So
The function will be
um,
at h
in
because that's our
here,
variable.
yeah, so at h, I'll make it clear. We have the function that we need to fill in here. We have the bounds that we need, which is h
Okay,
min,
okay, okay.
h max. Okay, so we have the bounds, but this function, to make the
The function we
optimization,
want to actually map is total CE, right?
yeah,
But then we
and
have to make it negative so we can get the actual maximum instead of minimum.
correct. So we got CE negative of that, and then uh, it's of H. So
And
that
then,
should work.
so pretty much, if we were to make that not minus, can you look at the graph?
The graph, if I run this one, okay.
That would pretty much be a downward slope instead of an upward slope,
If
right?
I, yeah, if I take out the minus here, it'll find the minimum, so I'll run that, and then it found the minimum down here. I don't know, I didn't start over there. I think it's because
Okay.
maybe the bounds were like here. I'll
I
zoom
thought it
in
would
the whole thing.
probably flip the whole graph, but I guess not.
Here, I'll clear the whole thing too. Don't know if that helps. Okay. Um, so now, yeah, I took out the negative. I can actually take out the thing that says at h, I believe, because we're not doing anything fancy with it. Uh, okay, so the reason we had the at h is because you have to make a at h and then negative for it to work. like over here, our solution was right here at h, the negative function. You can't make something negative without making it a function first, so that's why you need this thing here. Like if I were to just do negative, it wouldn't run. It would have an error with it. Um, but your question was, what if it's not negative? That means I can just plug the function straight in, the CE right here.
But then you'd still be finding the minimum.
Yeah, so when I run this, I press run, it actually shows it down here. It's it's saying that at 85, that's the minimum.
Okay.
So it highlights
That
the negative.
and
That
then
means
that
it's our
leftover dot
lowest.
at the maximum is there from previous runs,
Yeah,
right?
yeah,
Okay.
yeah. So yeah, that answers the question. What happens if it's not negative? It points out the lowest bound. Okay, so we'll go back to here.
It needs to
So
be
we,
at H so we can do the minus on it for maximum.
yep. And then we have this value stored here, like that's the high point, the max. Now we need to find the sorry, this is like the x value. X value. Now we need to find the y value. To do that, we just put in the original function, CE. Um, so we'll call this CE optimal, and this will be the y value. And we use the original function CE, then plug in the h optimal. So like we got the x value, the optimal x value, and now we need to
Okay.
get the
So what
y
that
value
code
back. So
says
put
right
it in.
there, the optimization code, that says this number, which is we're calling it H optimal, is going to be one number, and the output of the function will give you the maximum number from our function. So H optimal will just be one number, which is the max X value. And now CE optimal is CE, which is um yeah, okay.
Yeah, the original equation.
Doing the
Yeah.
math for our one best X value will return a number for CE optimal.
Yeah, so as an example, like let's say the x value is like the best height for this roof is 30 feet. I think we're in feet. 30 feet.
What is the
So
optimal cost efficiency for that 30
yeah,
foot
so
tall?
yep, the y value is the CE at 30 feet. And let's actually print it. So to print it, I'll press run. I don't think there are any errors. Or else to do like clear command line. Run. Okay. I'll take out the semicolon and it should print out. There we go. H optimal and C optimal. So at this point, debugging it, it does have all the functions correctly inputted, and then it can tell you the max and then the y value for that max.
Okay.
Okay.
So is
Now,
that it apart from printing the oh no, you got to make a plot and then the uh f print f stuff, but I mean that's kind of self-explanatory.
yeah, let me just put those in at the end. So let's plot it. Let's make a range of h's from the min to max, and then we'll CE range is going to pull that in, CE with H range like that. And then I think we can plot it. So plot H range,
As
CE
the x
range.
values and
Yep.
then the y values will be CE range. Okay.
Okay. I'm
CE
gonna.
range CE range is doing the math for all of the x values that we have defined in our range.
Yes. Okay, I'm gonna plot this. It should plot it as a white line. Yeah, there we go. And I'll start labeling stuff with it. I'll expand this out.
How do you add a dot to the max?
So we plotted the graph originally, and then we'll do hold on, and then plot the H optimal, and then the C optimal. Yeah.
And that's just 1 point.
Yeah, if I press play, it'll plot it, but we need to describe like what the thing is, so we can do, I think RO. There we go. And I don't like
It's a
red.
red and it's a circle like that.
Yeah, it's hard to see red. I'll do white. Okay. I honestly don't memorize what I have to think about how to plot with the styles. I just look them up. And then we do X label, and then you can call it roof heights in feet. And then Y label is cost effectiveness, CE. And if you want, we can do the F. So here's the copy and pasting F print statements at the very bottom. And that will print out optimal roof height, and it's a float, like a float to 2 decimal points, I think. I might be wrong. And then a new line so that you can print out the next line. And you're putting in H optimal and CE max. So if I press play, there we go. Oh, sorry, CE. I did. I changed my stuff here. Okay, I'm gonna do clear. This should be it. So I have the plot with a dot, and then it says H optimal 21 and C optimal 3.59 to the -4, and then it also plots it here with a f print f statement. Yeah, any last thoughts? We covered uh, how to get the CE function, plot it against a range of heights, which is derived from the angle. Then we got the max. Then we found the x value and the y value of this max, and then plotted it. And that's how you optimize something. You find the max or min of a function over a range of numbers.
Awesome. Thanks, Jared.
Awesome.